now we online with Berlin and Exeter. Everything is okay with the lines. Okay. So hello Berlin, hello Exeter. Good afternoon from Zagreb. Now we are about to start our non-parallel session of the Diderot Mathematical Forum. It is formed by one lecture from each city. And here in Zagreb, we are pleased to welcome Senka Maćešić and Nelida Črnjarić-Žic from University of Rijeka. Their primary field of research is mathematical modeling and scientific computing, especially in fluid dynamics. So today they will speak on backward in time probabilistic method applied to the Gulf of Mexico oil spill. So in this terrible environmental disaster, we'll see how numerical simulations can be very useful in describing behavior of very complex systems. So please, Senka.
Thank you. Well, I'm going to talk about our research that is related to this disaster, and actually the sequence of events that led to our research began in 2010 in South Korea, where in the shipyard of the Hyundai company an oil drilling unit was produced for Transocean, and then in the same year it was leased to British Petroleum. That oil drilling unit had the name of Deepwater Horizon, and that name reflected the fact that it was built to be able to drill in depths of seawater that were never been drilled before. So it had very, very interesting and new technologies embedded. It was dynamically positioned, it was semi-submersible, and it was considered very successful before that disaster, and it was even called lucky. They were referring to that Deepwater Horizon unit as the lucky one. And that was the case until 2010. In the February of the 2010, Deepwater Horizon was moved from the previous position of drilling to Macondo Prospect. Macondo Prospect, that was in the Gulf of Mexico, quite near the coast, and it went again all fine until April of 2010, when at April 20 at 9:45 p.m. Central Daytime, what happened is that some very high pressure gases rised through the drilling pipe up to the rig. They exploded momentarily, causing death of that moment 11 workers. No one else was killed by that accident, but those 11 workers just went missing. And that was how it looked that evening. What happened next is that, of course, the US Coast Guard firemen tried to extinguish the fire, and they were doing it for 2 days, when on April 22nd at 10:22 a.m. Central Daytime, the damage that fire caused on that unit was too massive. The unit just sunk, and when it sunk, then the rising pipe, the drilling pipe, got turned off. So it just what happened is that after that, the well that was 1.5 kilometers down deep in the water remained opened, and crude oil and natural gases just kept gushing from that well. And that was going on for next period that was really too long. They were trying to seal that well, but they didn't succeed until July 15th. So you have about approximately 3 months of massive gushing of crude oil and gases into the seawater and also into the atmosphere. The estimates are that about 5 million barrels of crude oil entered the sea, and even more gases went into the sea and into the atmosphere. That was actually the largest offshore oil spill in the US history, and this is how it looked. So it was really an extreme ecological disaster. The most evident ecological problem was the oil on the sea surface. So you had these oil slicks that were moving on the sea surface and polluting coast beaches that affected very, very strongly marine life, wildlife, affected the economy of that area, and even human health. So it was a very, very huge problem. People that tried to prevent this oil slick expanding were people in US Coast Guards and even in companies that were hired to do this job. And what is clear is that if you want to prevent extension of an oil slick, it would be good to know the direction of that movement. So they were using some known models that were available at that time, and it turned out that those models that they had the possibility to use were not really accurate enough. They had problems with that predictions. What happened is that at the same time as that oil leaking and everything, that pollution was going on, in the University of California, Santa Barbara, Igor Mesić, which is from Rijeka. He was born in Rijeka, but now he's working only in University of California, Santa Barbara. He was developing some new mathematical tools, really very, very new. New diagnostics that was meant to give some diagnostic tool for two-dimensional incompressible flows. And it was based on the average behavior of trajectories, and the idea was to develop indicator that could tell us if this average trajectory is hyperbolic or elliptic on average. It is something that comes from the dynamic system theory, and he was developing those tools. They showed that there is a possibility to define such an indicator, and such an indicator is actually just a determinant of the Hamiltonian of the average velocity on such a trajectory. And the idea is to plot such an indicator, and they called plots of such indicators hypergraphs. And what is interesting, that when you look at the value of those hypergraphs and plot those values, in the way then the blue and the red zones that you see on those figures are the zones of mesohyperbolicity, and the white and green zones are the zones of mesoellipticity. Then you can tell where there are mixing, where there's mixing, or there are other types of fluid flow properties. And when you carefully read those hypergraphs, you can tell the direction and the typical things that will happen. They used two things for this, get these graphs exactly for the Gulf of Mexico. One is that you need velocity fields, pre-computed velocity fields, and they were using velocity fields that were computed by hybrid coordinate ocean model that was given to them by the Naval Research Laboratory. So they were using those velocity fields. They made some 3-day averaging and plotted those graphs. And they were able to produce predictions that were very correct and really helped people that were trying to stop those oil slicks. So a complex theory from dynamical system theory, from theory of chaos, helped cleaning and preventing, at least at some extent, of those oil slicks. Also, the whole research was published, as you saw before, in the Science Express in the September of that same year. On the other hand, there was another very important thing about that pollution. One thing was happening on the surface. Something different was happening deep below in the waters of Gulf. And that was not only crude oil, but also gases were gushing out. And those gases, since the depth is large, they were pressured and they were not getting out up to the surface and into the atmosphere, but they actually remained dissolved and trapped in those depth waters. Those gases are hydrocarbons, so they are something that is very much good food for bacteria on the one side, and on the other you don't want such huge amounts of hydrocarbons that are not natural in those waters. So this is again a very important pollution issue. David Valentine was one of the scientists that were observing that part of the pollution. He is from the Department of Earth Science and Marine Science Institute at University of California, again, Santa Barbara. And he was one of those scientists that observed and measured that side of the pollution, taking water samples, analyzing hydrocarbons, analyzing bacteria found there, and everything else. So he also published several papers regarding that part of pollution. And he was, and everybody else was also wondering about what was really happening with that part of pollution. There were two things that were strange. First is that no one really had a good idea of how those, they are calling it plumes of those hydrocarbon, should be moving. They expected to have a river of plumes deep in the Gulf that will just go away from the source of pollution, from the well. But instead, they were more like clouds that were moving in directions nobody expected. And what was even worse or stranger is that after some time, hydrocarbons disappeared, and it was just too soon. The only clue that was some idea, you could get some idea what was really happening there, was oxygen depletion. You see here these red zones in the depths of the Gulf. These are the zones of oxygen depletion. So a much lower of oxygen concentration was there after the process was over. And David had some idea of what happened, but he knew that he can't reproduce the model, reproduce the entire story by himself. So he went to Igor to add the fluid dynamics component of the entire story. And then what Igor and he did was they began to put a mathematical model of that whole process, and then they included us in that mathematical and numerical modeling of the whole story. The goal was also to produce a paper for the proceedings of National Academy of Science. That was a special issue at that time. And about the research, now, second speaker.
Okay, it's everything okay? Hello. Now I present you a mathematical model that was actually a base of our research. In our research team, there were also scientists, Sofie Loar from University of California, Santa Barbara, Vladimir Funoberov, that was in this time at that moment, a chief scientist in AIMDA Incorporation, and Stefan Ivić, our doctoral student from University of Rijeka. This, in order to establish what happened with all those hydrocarbons, bacteria, and oxygen, we developed a two-dimensional time-dependent model, including water motion, and also the hydrocarbon inputs that feed the bacterial metabolism. So it turns out that such model, which combines the physical, biological, and chemical effects, actually made with such a model, a great improvement in clarifying the whole process is achieved. The entire Gulf of Mexico was modeled on two different levels. A two-dimensional approximation was used, and the dynamics of fluid particles was modeled by using the simple differential equation xy is equal to v, where v is some known velocity field. The distribution of velocity vectors are actually obtained by using the same model as previously Senka mentioned, the hybrid coordinate ocean model in Naval Research Laboratory, and the researcher Patrick Hogan also was included in the whole work. Here you can see the visualization of the velocity vectors at one moment, and also the movie where you can see the dynamics for the obtained velocity field. You can see this circular motion, water motion is present. So with this part, with this dynamic equation, we can model actually the water dynamics, but these water volumes actually carry bacteria and hydrocarbons. And what have to be included now in the model are those changes of hydrocarbons, bacteria, and oxygen changes. The daily input fluxes actually consisted from 26 hydrocarbons, and each hydrocarbon was consumed by one bacteria species type. The list of hydrocarbons is here in the first table column. So the product that was developed when the bacteria, during the bacterial respiration, when they consume actually those hydrocarbons, the product are some extracellular intermediate metabolite, which we refer to as secondary compound, and these are consumed with other bacteria species. So this means that we have, in summary, 26 hydrocarbons, which are actually primary compounds, 26 secondary compounds, and 52 bacteria species, and their changes has to be modeled. This means that for each hydrocarbon, we have actually 4 chemical reactions that can be then mathematically modeled by using the simple differential equation. This here, the CJP actually denotes the primary compound, the CJS denotes the secondary compound, while rho, J, P, and S denotes the primary and secondary bacteria concentration. The growth and decay terms are on the right-hand side of these equations. The first one, for the growth of the primary compound, is modeled by the term CSJ, and these are actually the hydrocarbon inputs from the well, and these are models by using the Gaussian distribution around the Macondo well. Here, x0 actually denotes the coordinate of the Macondo well. The amplitude of of this source term are determined from the daily flux estimates. The bacterial growth, here, Gj, are simply supposed to be proportional to the instantaneous bacterial concentration with the rate Kj, where Kj is obtained from the mass doubling times. For our bacteria, for each bacteria type, the mass doubling time is different, and they vary actually between half of the day to 3.5 days. The decaying process is supposed to be similar, and it is modeled again in quite simple way. We simply suppose that the rate of decay is proportional to the own bacteria concentration. Here the mu J denotes, similarly as before, the rate of bacterial decay, and this term is determined from a mass halving times. For our bacteria species that were considered, the mass halving times were about 2 or 3 weeks, much slower than doubling times. And finally, the total oxygen depletion can be modeled by using the following differential equation. You can see that all growing and decaying terms actually appear in these equations because the oxygen is depleted during the bacterial respiration as well as during the bacterial decay and their dying. In what follows, let's consider just one primary compound, for example, methane, and focus on just one water parcel, which began on April 20 its trip around the Gulf. Pushed by water current, at that moment, the methane concentration as well as bacteria and oxygen concentration have normal values. Then the water parcel began its trip around the Gulf, pushed by water currents, and then after some time, this observed water parcel came near the Macondo well, where it obtains a large hydrocarbon input. That means the methane concentration grows rapidly, while at that moment the bacteria and oxygen concentration were still normal. However, the bacteria start to grow rapidly. They have the bacteria type have their preferable food, and its growing lasted for a while. The bacterial growing process can be described by the following chemical reaction, and as I already mentioned, the exponential growth is supposed. The doubling time is about 3.5 days. After some time, the bacteria eat and consumed all the methane, and the methane concentration returned to its normal values. However, the bacteria concentration became 100,000 times larger than normal, and at the same time 3% of oxygen was depleted. Then the dying process, actually the bacteria consumes all the food, all the methane, and the dying process of the bacteria started. The dying process can be described by the following chemical equation, and exponential decline is also supposed. However, the bacteria lives in abundance for a while, since the dying process is much slower than the growing process. So, after some time, what happened? Almost everything returned to normal values. The bacteria concentration, the methane concentration returned to their normal values. However, the 9% of oxygen was depleted. And what can we say? If we track an individual water parcel, we can conclude that if it comes near the Macondo well, it actually receives a large hydrocarbon input, and as a consequence, a bacterial growth, some bacterial growth, and oxygen depletion arise. But if we consider more water parcel, and we track more water parcel as they advect, reveals that actually many parcels come into contact with hydrocarbon inputs on multiple locations. Here is one example when the water parcel come near the Macondo well twice. It receives the large hydrocarbon input 2 times, and the consequence of that is much larger bacterial growth, because the water parcel was actually previously exposed to hydrocarbons, so the bacteria abundance was larger than in the beginning, and also the much more oxygen depletion arise. This effect is referred to as dynamic auto-inoculation effect, and it occurs when hydrocarbons are introduced into previously exposed water parcels. The bacterial abundance, the relative abundance, is also different if the water parcel is exposed to hydrocarbons inputs in multiple locations. And when we want to obtain a spatial distribution of our bacteria's hydrocarbons and oxygen, we use the following procedure. First, we define a uniform computational grid, and for each grid point as a final point, we track it backward along a trajectory by using the fluid motion dynamic equation, and track it to the initial point. By the initial point, we mean its position on April 20. Then we track again the water parcel, but now forward in time. When we track it forward in time along the already evaluated trajectory, we include all the variables in our computation. And at final time, we evaluate actually the bacteria concentration and all other concentration on the uniform computational grid. The result of the spatial distribution on one chosen day, June 30, is presented here in this figure. In the similar way, we also determine the hypergraph maps. So we again use the uniform computational grid. We evaluate the trajectories back for 7 days and evaluate the mesovelocities and also the hypergraph values. We evaluate from that the mesohyperbolic zones, which are here indicated with blue color and red color, and mesoelliptic zones, which are here denoted with green color. What we can say when compare spatial distribution and hypergraphs? We can say that the blue mesohyperbolic features indicate in hypergraph map accumulate high bacterial density. You can see here the blue part, the blue color. If you look at the blue part of this graph, you can see that the bacterial concentration is quite high around it. The similar conclusion can be made for red colored parts of this hypergraph. So the mesohyperbolic zones actually act as convergence zones for all advecting reacting fields. On the other side, green zones actually In the green zones, the flow field causes swirling, recurrent motion of the water and associated bacterial population, a large bacterial population. The described spatial distribution can be are compiled in this video material, and during the video I'll say something about final results. You can see on the video the four different variables are tracked: the hydrocarbon concentration, bacterial abundance, respiration rate, and oxygen anomaly, and the time. You can see here the time prospect. So analysis of our model simulation shows that mixing feature of the flow field influenced the chemical and microbial distribution at plume depths. Auto-inoculation appears to have played an important role in suppressing large hydrocarbon inputs. Because discharge from the well continued for so long, almost roughly half of the total eruptive hydrocarbons actually entered the pre-exposed waters. Crucially, the accelerated respiration resulting from this event drove down the levels of hydrocarbons and stabilized the overall respiration rate. And you can see, as Senka mentioned before, you can see that some clouds of bacteria actually appeared in those deep waters, and not that they do not behave like rivers as was supposed previously. The other movie presents the oxygen depletion, and here the results are actually compared with the measurements. Here the red squares indicates the disagreement of measurements and model, while the red squares, you will see it, the red squares indicate the concurrence between model and our numerical, between model and measurements. And you can see this here, the percentage near the red and green square indicates how much points of disagreement and concurrence we have. Finally, you can see that at the end we have about 70% of agreement point. That's all from me. And now Senka will additionally present some numerical results, additional numerical results. Thank you.
So we did our research, produced the publication, and then we went back to the research and tried to see what can we improve further in that whole computation situation. So what is the reason why we can do the ordinary differential equations, go backward in time to track to construct the trajectory, and then go forward in time to compute the changes in bacteria, oxygen, and other things. The reason is that there are, as we all know, two possible mathematical approaches to the entire problem. One approach is that you want to track this passive tracer and compute their concentration. And one possible approach is to do just a parabolic partial differential equation in the entire domain. So in one possible computational version, you can take a domain, in our case, the Gulf of Mexico, for example, at depths of 1 kilometer. then decide to do the computations for some interval of time, in our case again from April 1st to October 1st in 2010. Do the computation for these passive tracer concentrations, and here is the first difficulty. We have to compute this for different 105 density fields, so we have to solve 105 different parabolic equations, partial differential equations. We know from the talk of Nelly why this so large number of density fields. We have to solve this parabolic partial differential equation, where this part and this term is due to the known velocity field. This part vanishes because we are looking at an incompressible flow. This part are the source terms. Source terms consisting of, as we know, hydrocarbon gases, the respiration process, and the bacterial decay process. And the right-hand side, which in general case appears, and this term is due to diffusion. So A is the diffusivity tensor. Why we were doing then initially ordinary differential equations is because we computed diffusivity tensor values based on those velocity fields, and we knew that it can be okay, then the results can be okay because we knew diffusivity tensor has low values. So the first approach was in our computation was to simplify somewhat the model and neglect diffusion. Also, we of course have in the parabolic partial differential equation version of model treat a boundary, and this is again one source of difficulties. We have a boundary that consists of coast, meaning a contact between the seawater and land below, not really real coast of this gulf, and also the open sea, the exit of the gulf towards the ocean, the Atlantic Ocean. So there are many difficulties if you take such an approach. Also, one relatively simple thing is to guess the initial values for the passive tracer because we knew the concentrations. So this is one possible approach, and it is known that it is not the computationally most efficient thing. There are many problems if you want to, for a long period of time, do computations with this approach. You have to have some quite good boundary conditions, or take a very large domain, and this makes computation very expensive, long lasting and stuff like that. So an equivalent formulation is of course that you use stochastic differential equations. So if you use stochastic differential equations, then you reformulate that initial problem to this Cauchy problem, where you have three equations, but one can be again dismissed because of the incompressible flow. The meaning of the first one is that you can compute trajectories through it, and this is what we saw before. The difference is in the last second term, because when you have the stochastic differential equation, you have to put some perturbation in the trajectories. And the last equation is for the density changes due to oil spill, to directions, and everything. So first is the one that you compute backward in time, and the second, the last, third actually, you compute forward in time. This is something that is legal to do. It is proved that it's correct way to do the solution of this stochastic differential equation, and it gives you a very important advantage in computations. It makes computation faster. Nelly explained the way you can compute in the domain. You take a very regular domain that of your interest, track the parcels backward in time. You don't have any problem with where the parcels were before. Reconstruct the entire processes along the parcels, and you have this great computation. So one is, of course, that you, at the end, if you neglect diffusion, then you can just do what we did before and you are fine. But if you take the diffusion into account, you have to do the stochastic equations version, and you then ultimately have the solution only as expected value along all those trajectories that you computed for one position. So this is, you take one initial position on the water parcel, your interest is to evaluate it at time t and position x, and you reconstruct its initial value, and you add also the perturbed section, and you get the evaluation of this. So final question is how you treat the diffusion. Actually, 3 possible ways to treat diffusion. First is to neglect, we saw that. The second is to use Monte Carlo. Then you take n independent paths, randomly selected, just make a simple averaging of the solutions you get in this way. And it is well known that if you use Monte Carlo, then the convergence is a square root of n. So this is not a bad way to compute everything. The problem is that for every point on the grid you want to compute, you have to multiply the computations by this n. That is a number of different paths for each point. We made several computations to see what are the effects of diffusion. What if we switch on as weak diffusion? What if we take medium diffusion? What if diffusion is very strong? We see very strong diffusion effects, obviously, on this figure. And so taking count the results and also what we needed that diffusion is in that part of Gulf of Mexico, we decided to stay with the medium diffusion approach. And finally, so there are some comparisons between what if you don't take diffusion and what if you take a realistic diffusion. And finally, there is a third approach. The third approach is again through stochastic differential equation. The fundamental difference is based on this article of Igor Mesic and Sophie Loire, which says that you don't have to use Monte Carlo, and you just have to use a finer grid, and instead of for each point in the grid compute a different set of n trajectories, then you can use the points on the grid and use a spatial filtering method. So the result is that you define a spatial filter, you take an epsilon that enables you to use it in a very controlled small zone around the point of interest with an essential support of your choice. You use this grid point, you use such a weak stochastic differential equation solver, get the results, and the final important result is this theorem that says that if you do all these things not through Monte Carlo but through spatial filtering, you again get good convergence results. And so we also did the computations with this third version with no diffusion comparison, and what if we do the space filtering. Thank you.
So thank you for this nice lecture. Since we do not have time left, we can postpone our discussion to the round table. So